So good morning and thank you for coming. We're going to do the main effort today and go through the estimate of effective critical set of Naber and Valtorta. I am not going to do all the technical details. Let me remind you what we are talking about. We have a harmonic function in the unit ball. And in my notation from Tuesday, we're looking at the set of the points, say in the half of the ball, for which the upper frequency of the function at point x and this radius r is larger than or equal to 3. This is the effective critical set. And remember that we know that if point x is in the real critical set, say in 1/2, then with our normalization, this is at least 4, the upper frequency of u at this point. We subtract the constant part, the linear part is 0, so the first term is at least quadratic, and in my notation frequency is 2 times the vanishing order. So critical set is definitely inside the effective critical set. Using our comparison of the frequencies, you can also show that if you take a small neighborhood of this one, there is a small constant, but fixed, such that if the distance from x to the critical set of u is less than this constant times r, then x is in the effective critical set. So we have the critical set with some small neighborhood inside this effective critical set. And the result that we will discuss, at least the first hour today, as I said, it's result of Naber and Valtorta. Let me add the theorem. It tells you that if we're in this situation and say the frequency on the large scale is bounded by capital N, then we can cover this set by balls of radius r and control the number of the balls between. Or if I'm in high dimensions, better to do it this way. You can cover this effective critical set by balls such that sum of the powers of these balls, the radii to the power d minus 2, is bounded by constant turn squared. and this Si will be of order R. So the volume of the effective critical set is bounded by this one. We believe this critical set is a nice set of codimension 2. And if you have a tube around this set, its volume should grow like R squared. I will do some computation in dimension 2 for harmonic functions. And as far as we believe, there should be a much better estimate for this case. It's not clear if it was to have much better estimate, because the powerful thing about this one is that you can extend it from harmonic to elliptic. And in this approximation of elliptic solutions to elliptic equations by harmonic functions, you lose a lot. So even if you do a much better for harmonic case, it's not clear if you can extend it to elliptic ones, but this, up to this constant, you can change this constant and still have results like that for elliptic equations, but we're not going to do that. I will skip many technical details, but let me do one nice computation here because it's simple. I can do it on the blackboard, relatively easy. We talked about it last time. I mentioned that if the frequency does not change much, it means that it's integer, and in a sense your function can be approximated by the corresponding term in the expansion over homogeneous harmonic polynomials. Let me do a simple computation here. It is the same in any dimension, actually. Suppose that the distance between the frequency and 2 times integers is epsilon. Epsilon is something between 0 and 1. And I want to estimate the derivative of the frequency at this point. We'll see what I get, but I believe I'll get something like that. So when I staying away of the twice integers, you know that this function decays when R is decaying or increases with some fixed speed. Okay, so the computation is here, and it should show you that this frequency function is not so bad. Even in higher dimensions, for harmonic case, it's a simple object. I don't know if you checked for yourself that it's increasing. We will see it right now. Take the derivative of this one times R. And let me assume that for my particular R, the normalization such that this is 1, so I don't write it here. And when we take the derivative, this is derivative of this one times that one. Minus the other way around. Here we'll have two equal terms, but I'll write them using different indices. Now we just look at the pairwise products. And you know that when n is equal to k, you'll have the same coefficient in both of those. They will cancel, so what is left is the sum when k is less than n. I'll have 4k squared plus symmetric term for n squared minus 4 and symmetric term minus 8. Definitely nice positive function. And we want to say that it's not only positive, but there is a nice estimate. So I want to now compare this to the following quantity, let L be positive integer. We'll look at the following expression. Frequency, this is nu xr minus twice integer times this one. With my normalization, you can write it as some, let me think, I want n to be larger, so let us write n here, 2n minus 2l, an squared r to n. This is the first term, and the second one is 2l plus 2 to k, ak squared r to k. When we open the brackets here and look at pairwise products, it's easy to see that the terms with the same index, when n is equal to k, they will have a negative factor. So I can forget about those. And write that this is bounded by sum where k is less than n to n minus 2l to l plus 2 minus 2k plus and now it's a simple exercise to maximize this product using integer L. You see that to maximize it, you should take L that is equal to 2L that is equal to n plus k minus 1. And then you get that this is bounded by 2 times n plus k, sorry, n minus k plus 1 squared. But also there is no term when n is equal to k. That is important. And now we say that this is less than, I guess, 2 times 4n minus k squared. Either 2 or 4 here, you can check it. When n minus k is equal to 1, it's our worst case. I'll have 4 times 2 and 4 times 2 here. So this should be the inequality. And going back to my lemma, what we did, we took L that is closest to our frequency, and we proved that this derivative is larger than 1/2 times n minus 2L L plus 2 minus n. Hopefully this is exactly this epsilon here, and then 2 minus epsilon over 2 here. So it means that if your frequency is non-integer, and remember frequency is a monotone function, so when you change the radius, it is decreasing. At some moment you pass the region where it's close to an integer, but if you pass this and you're on some positive distance from twice integers, you know that there is some fixed speed of decay. So color is following there are epsilon and constant c, such that if your frequency is less than 2n minus epsilon, then when you drop multiplicative factor c in the radius, c is less than 1. So either you're already below this and there is nothing to prove, or you're above this and you know that the distance to your twice integers is at least epsilon, and then there is some speed of the derivative when you multiply it by r, and gives us your multiplicative factor here. Good. And these constants are explicit in Naber-Valtorta work. I think you can take this c like 1 over e squared or something like that. You can do the computation easily here and see what the constants are. I'm going to talk a little bit about the second idea, and I also mentioned it last time. If you know that your function looks like a homogeneous harmonic polynomial, and it happens with two centers, then you know a lot about this polynomial. But let me first do the following. So suppose that we have this with some small constant C0. Once again, it could be done explicit. Then, as we already know, this is close to twice integer. And the new message is that if you take a polynomial of this degree, that is the term in the expansion in homogeneous harmonic polynomials of the function, it will be a dominating term. So for any C1 is another small constant, but larger than C0. Then in this interval, what we will have is that L2 norm of function and the harmonic polynomial of degree L is bounded by constant times epsilon. So this polynomial gives you the big part of the norm of the function with all spheres between those two. And it looks like a interesting statement, but once again, it's algebraic thing, right? I can forget about harmonic functions. I know that n is a function given by this dependence on R, and I'm trying to check what happens, what is the dominating term in this expression if this difference is small. So it's a pure algebra that you can ask high school student to check if you have a good high school student by your side. So what is also true is that there is an estimate for the gradients. That is, but this one will be like that. And now let us go to dimension 2, because non-constant homogeneous harmonic polynomials in dimension 2 are very nice. They have only one critical point. And this is a difference between dimension 2 and higher dimensions. That the other difference is that in dimension 2, L2 norm and the infinity norm of your harmonic polynomial are comparable. If you want to do more careful estimates in higher dimensions, you should know what is the maximum of your spherical harmonic. We know that, but it grows with the eigenvalue, with the degree of the polynomial, and you have to track it carefully. In dimension 2, your harmonic polynomial is basically cosine function on the circle, and the L2 norm and the infinity norm are comparable. So in dimension 2, in this situation, if this is less than epsilon with C0 small enough, then for any t in between, so you have those two cycles where the drop of the frequency is small, and I'm saying that you can take two cycles like that. It's what I tried to write over here. So C1, this is C1R, this is C0, yeah. We have that there are no critical points here. And the reason is that your function is close to this polynomial, and this polynomial has no critical points. So, but moreover, it turns out if you work carefully with this expression for the frequency function and do your estimates, you can estimate the critical radius. You can estimate how far you need to go from point Y to have a ball where the frequency will be larger than 3. So your point is not in the effective critical set if your parameter is like R, that is our scale, divided by, sorry, L, where L is this integer or twice integer. Let me try to use these ideas to explain how to cover the effective critical set in dimension 2, and then tell you what is the difference in higher dimensions. So, yeah, let us first do it in dimension 2. There is a definition of a good ball that is the same in any dimension. So I want to define what does it mean that this ball is good for my function on level L. So L good form Q. If epsilon L good, if for any point in this ball and this radius R, we know that the frequency, upper frequency of U at Y on level R is less than or equal to L minus epsilon, to L plus epsilon. So we want this inequality not only for the ball, but also for every ball of the same radius centered at Y. And this is good. First, I claim that if we start with L large enough, then our half ball is good. Well, probably half is too much, but 1/3. Don't need to add ones here because our frequency is always at least 2, right? So there is no point in adding a constant if I'm allowed to multiply it by any constant. It's a statement from our first lecture that we control the frequency in nearby balls by constant times the frequency here. So if we start with large enough L here, we know that this ball is good. And then there is an induction step, or half of it first. If Vx0r is good, then we can cover it, or the effective critical set in this ball can be covered by finitely many balls, such that for each of them, as J is equal to R, or the upper frequency of U on this scale is less than L minus epsilon, and for any Y in a larger ball, we have some control like that. So we want the corresponding radius there to be not much smaller. So if I will go at Ck/10, I want this to be bounded by L minus epsilon. So this is a half of the induction step, because for the moment we cover the ball by new balls and we drop in frequency by 4 epsilon. So near integers we drop carefully, but then from here, using our corollary, we can drop to L minus 2 plus epsilon by a constant scale, right? So we know that each ball here can be covered by finitely many balls, where instead of 2L minus epsilon, I have 2L minus 2 plus epsilon. So let me write it down. if I take this ball then we can cover this one by finitely many there is a constant. Do I know what the constant is? I'm not sure. Let me. It's a small constant here. C3 S yod. Such that each of those is epsilon L minus 1 good for our function B. So when here we know that if we decrease the radius, we will go near the next integer. We're not sure we're near the integer. It could be that we're below the next one, but then we don't do anything if we're below the next one. If we're not much below the next one, we go to the next one. And we need just finitely many balls here to cover our ball. Each of them will have a radius comparable to the radius of this ball to drop the frequency. So this is because of the lemma that we actually did computation for, showing that this is the case. And if you now believe in all those three claims and do the math, you will see that at the end, what happens? We cover our ball by smaller balls. Either we are already on this scale of radius r, and then we leave this ball as it is, or we have balls that are covered by good ones and continue the induction. So in each step, we leave some of the balls as they are if they already have this small radius r. If they are larger, we continue to do the procedure. At the very end, remember we're covering the balls. Yes, I should also say that I can take those points in my set. The centers of the balls are in this effective critical set. At the very end, you will look at the balls for which the frequency is small, and since you're in an effective critical set, it will mean that you're trying to look at the balls of the radius less than r. But we agree that on each step, if we reach radius r, we stop. What I'm saying is almost true. I believe you have to multiply this by a constant here to make it really true, but it's a technical thing. Let me try to explain why you should believe in claim 2, at least in dimension 2. In a high dimension, it's not true. And the thing is how to cover ball by finitely many in this way. So let us think what happens. We have, let us think of, normalize this ball as a unit ball. We have a unit ball. We know that it's epsilon L good. and at each point x of our effective critical set, we define R of x such that let me say it is equal to L minus epsilon. I know it's a continuous function, it's not a constant in an interval, otherwise my function would be a polynomial. So there is one particular radius where I reach this one. So at each point we look how small we should go for our frequency to drop to L minus epsilon. Since our ball was good, we know that this, so I realized everything to scale 1, this was bounded by 2L plus epsilon. So there are two things that can happen. Either this R is large enough or it is small. If it's really small, then we have two scales. So the difference between the frequencies is not epsilon, but 2 epsilon. Never mind. So we know that if at some point R is small, then we have a picture like that. This was my unit ball where I want to cover everything. I have a point here where my function looks like a homogeneous harmonic polynomial on this ring here. And the big radius here is a constant, right? If the small one is dropping far enough, what we know is that I have to divide the large radius by a constant, multiply small by a constant, and inside this ring I will have a control. And what we're saying that there is no way you can get this picture with two different centers that are not too close, but on the distance that is like a constant times this radius here. Otherwise, your function would have to look like two homogeneous harmonic polynomials, and in dimension 2, there is no way it will do it. You have to be a little bit more careful and choose this ball so that it's a local minimum. Remember, I want this property that when I am around this ball, the radius is not much smaller. But it's a weak notion of minimum. If you will think, what does it mean that we don't have a minimum? You can easily construct a convergence sequence where you have smaller and smaller things. And also, we don't care what happens if this R is smaller than our scale R. We always stop there. So what I'm trying to convince you, and the fact that we can cover this ball by finitely many balls, and each of them will be either on this scale R, small scale already, or we will have a good ball for the next integer. In higher dimensions, there is no way you can do it in like this, and the reason is that you can have a subspace along which your harmonic polynomials are just constants. But what happens is that if you have a homogeneous harmonic polynomial, it depends at least on two variables, and there is probably a subspace of codimension 2. So instead of saying that you can do it with finitely many, you try to control the sum of the powers d minus 2 of your balls, and see that it's is bounded by a constant if we normalize everything. And then you do it many times. Yeah, I'm not correct. You will have to actually bound it by a constant to the power L, where L is the parameter of these good balls. And then when you sum it up in higher dimensions, you will get constant to the power n squared, because summing those, and in one dimension, in 2 dimensions, what we get is constant to the power that is frequency. This was the most technical lecture. Sorry for that, and we'll try to be less technical after the break.